Hello everybody, welcome to our second video and the first video that we're going to do with the intention of watching this in class. And so I'm pretty sure I've talked about this with all of my Physics 20 classes quite a bit, but just in case you don't know our why, I want to talk about our why for a little bit here. I probably talked about this in class before we started the video, but let's do it again. The reason why we're doing watching a video in class rather than me teach the whole group is for a couple of reasons. Probably the biggest one is that this allows a bit of more of an individualized learning. And maybe that seems kind of weird that you're doing individualized learning and you're watching on an iPad or on a tablet or on a phone. But what ends up happening often in school is we end up teaching and everybody gets the same lesson all at the same time and we all have to go the same speed. And we know that not everybody learns at the same rate. Some students, they need a little bit longer. They may need to ask a few more questions. And other students, they may be getting bored because they already understand and they want to go to the next example. And by doing this, which is known as asynchronous learning, this is going to allow you as a student to basically go at your own pace. So for example, let's say that we're doing an example, a math type example, and you didn't fully get it. You got a little lost. You weren't sure where which number came from. You can pause the video and rewatch. Whereas in class, sometimes when that happens, the teacher kind of moves on and you fall a little behind and you're looking at the last example and now we're on the next example and it's starting to spiral and all of a sudden you're completely lost, right? And you start to shut down. And I'm sure people have had that happen before. And that's not a good thing, right? We want to avoid that. Sometimes students, they don't want to put up their hand and ask questions. Sometimes for fear of feeling dumb, because you're not, obviously, right? But you don't want to look like you don't know what you're doing in front of the class. And some kids, they don't want to ask questions because they don't want to slow everybody else down. They look around and they see 30 other kids who are all going fine, and they're like, okay, I'll ask later. And maybe they don't actually ask later, right? And so they don't want to stop the class because they don't want to be the one kid, right? And I mean, at first I'm here to tell you that that's okay, right? I mean, we know that kids learn at different rates in different ways. It's like that one cartoon I hopefully showed you of the teacher who asks all the animals to climb the tree, and the monkey has got different skills than the fish, who's got different bills than the seal, right? And so that's my goal here, is by doing this asynchronously, meaning that you can do this on your own time at your own pace, you have the ability to stop the video, fast forward the video. One of the things I'm going to encourage you guys to do is when you get stuck, press pause, put up your hand, and let me try to come explain it to you. Because we know that kids don't generally learn best in a lecture type scenario. They usually learn best in one-on-one scenarios. So, anyways, that's our why. We've probably already talked about this lots. You probably could have fast-forwarded through this section, so I'm going to get started now. 3 minutes in. Kinematics equations. This is our second topic. Our discussion for this unit is about kinematics, which is all about putting things in motion and trying to describe them mathematically. And so far we've learned about 4 different terms, 4 different variables. I'm going to discuss them for a bit first. The first one is distance, which we represent with a D, or displacement with a D with a little hat on top of it. And this is known as a vector arrow, which means that we have to know what direction you're traveling. Speed and velocity, kind of similar. One is V with a hat. The hat meaning that when you talk about a velocity, we now know which direction you're moving. So if I tell you you're moving 100 kilometers an hour, that's a speed. But if you're going 100 kilometers an hour west, now it's a velocity. Acceleration is generally considered to be a vector due to the fact that, I mean, you need to know which direction you're accelerating or decelerating. If you might be speeding up, you might be slowing down. You might be speeding up but going backwards. So direction definitely matters for acceleration. And time is a scalar, the opposite of acceleration. Scalar is the opposite of a vector. And scalar means that not only do you not have a direction associated with it, but like in time's case, like you can't put a direction on it. Even though you could try to in a distance example, like you could try to attach a direction to a distance, you can't on time. You can't on mass. You can't say that something weighs like 14 kilograms north. That doesn't fit. Temperature doesn't work that way either. So there are some things that are vectors and some are not. Hopefully that's familiar to you. There are actually 2 formulas that we worked with yesterday, or whatever our last day was, and you've also hopefully learned in Science 10. And those formulas are V equals D over T. And sometimes we add a few things. Sometimes we put the little vector hats on top. And sometimes we put a little triangle in front of these things. And if you're not, pardon me, if you're not familiar with the triangle is the Greek symbol delta, and it means change. That's the Greek kind of concept behind it. And so often we will use that to refer to a change in a distance over a change in time. So that's one formula. And then the second formula, hopefully you're familiar with, is that an acceleration is known as a change in your velocity over your change in time. And these formulas here, I have a couple of words I want you to know. The first one is that this formula here is known as uniform motion. And we use that word to describe anything that's going the same speed. The same kind of is why we use the word uniform. Uniform is a scientific word for things that go the same. Whereas when you have an acceleration, you have non-uniform motion. And we can have your non-uniform motion in 3 different ways. Now, 2 of the ways you're hopefully familiar with. The third one we're going to discuss later in the course. But the first way you can have non-uniform motion is you speed something up. You step on the gas in the car and you go faster. That's non-uniform motion. You're getting faster. Or the opposite of that is that maybe you step on the brakes and you slow yourself down. That's also non-uniform motion, right? That's where you're decelerating. The third one is one that we're going to discuss in an entire unit later in the course. It's known as your centripetal acceleration. We have to put a little C in the corner next to it. And centripetal acceleration is for when you start going around in circles. And you might actually be going the same speed. You might always be going 25 meters per second. But because your direction is changing and acceleration is indeed a vector, there is a change happening, and that circular motion is known as centripetal acceleration. And you've probably felt this before if you've ridden on like a merry-go-round, or say you're in a car and someone takes a corner a little bit fast. Oh, you might have heard that sound. A video just finished uploading. Anyways, if you're going around a corner and you go a little bit too fast, you might find yourself like thrown into the door of the car. You're feeling centripetal acceleration kind of at that time there, where it's a center-seeking force. Anyways, that's acceleration. Hopefully that's something that you're familiar with, these terms here: distance, displacement, speed, velocity, acceleration, and time. So what we are going to learn today are the 6 kinematics equations. And really, a couple of them you already know, because we just discussed this one right here. And I want to point out, if you ever use the V equals D over T formula, you must, super important, big stars, you must only use this formula when you are going the constant speed. If you are ever speeding up, you can't use this formula, or slowing down, or going in a circle. Okay? So this is actually a pretty rare formula to use, this first one. You have to undergo circular motion to use the first formula. The remaining 5, though, all involve some sort of change in speed. And so the remaining 4 formulas that you're probably not familiar with involve VF and VI. See that? VF and VI. And VF stands for your final velocity. VI stands for your initial velocity. And that's just a way to kind of keep track of your start or your end speeds, because we know you're speeding up or slowing down. And so this formula right here, if you can't tell, it's VI times T. And this formula here is VF times T. This formula has a VF and a VI, and so does this one right here. And so my goal today is to go through and show you how to use these formulas a little bit. What I'm going to try to do is, between every slide, or like every example, I'm going to do a little bit of a cutscene where it kind of fades in and out. And hopefully that'll kind of let you know when we're done a problem. And if you're fast forwarding through the video, because you've got the example and you want to move forward, maybe try to look for those cutscenes, and hopefully that'll help you a little bit if you want to try to fast forward. Because I think that's an advantage, right? If you want to go at a faster speed, you can do that now. You don't have to wait for the group. So, okay, let's do our first example. And before I do the example, though, I just thought of something. I need to remind you that although physics, a large part of physics, yes, involves using math to try and make predictive calculations about how things work, right? Physics is all about discovering how things work. I want to make sure it's clear that physics is not just going to be about doing math. That is an important part, but that would be like saying that hockey is just about skating. I mean, yeah, if you want to play hockey, you better know how to skate, but you should also know how to pass and all that other stuff. Boy, I can't think of any other things you do in hockey other than skate and pass and shoot and anyways, you get the point here. Hopefully you get the point. The idea being that, yes, you need to be able to do some math equations, but please don't think that like this is all we're going to do. There's a lot of theory and problem solving and critical thinking involved in physics, which is good. Those are skills we want kids to have. All right, anyways, off my soapbox, and let's do an example here. There's a train that's decelerating at a rate of 4.5 meters per second squared. It takes 20 seconds to slow down to a speed of 2 meters per second. We want to know how much stopping distance it needs. Well, you're often going to be given scenarios like this, word problems. That's a common thing we're going to start with. And so one of the strategies you may want to use is to record your variables. For example, as soon as I see this number right here, 4.5 meters per second, I know that that is an acceleration. And I'm going to actually write it as negative 4.5 meters per second squared. And I'm going to just pause for a quick second. I want you to think, why did I make it negative? I don't usually use a lot of wait time on videos when I teach to a computer screen, but maybe pause for a second here and think, why did I make it negative? And here's the answer. It's because you were decelerating. You're slowing down. And so that's really important that we actually use a negative number, because if you use a positive number, you're speeding up. Okay, I also noticed that it said we took 20 seconds. So that means we have a time, because 20 seconds is a time value. And it also tells me that we've got a 2 meters per second, so that's a velocity, is 2.0 meters per second. But I gotta be more specific here. What kind of velocity is this? Because this is not uniform motion, it's slowing down. And you'll notice it says it slows down to a speed. That word right there, to, is kind of the essence of what we're going to be doing in physics. You're going to be asked to solve some sort of puzzle or problem, use critical thinking skills here, and you have to be able to understand that when you're slowing down to a speed of 2 meters per second, this implies that it's your final velocity. It makes a difference. All right. Last thing, we've been asked to try to solve for a stopping distance, so I'm going to use blue as a color here, and that's our goal. We want to find our stopping distance. So what we'd like to do now is try to find a mathematical formula that involves acceleration and time and velocity final and distance. And if you go back here, we need a formula that involves velocity final and time and acceleration and distance. And this guy right here is a good formula to use. It involves all those variables. And so again, that's actually part of the problem solving, is you being able to decipher what information do I have, and what can I do with it. And now that you realize that this is the formula to use, let's give it a try. D equals VFT minus 1/2 AT squared. I'm just going to double check. Yeah, it's the minus formula. One formula involves minus, one involves plus, and they change the final and initial velocities around. Okay, so the next step is after you identify your formula, and by the way, I want to show you what I'm expecting out of written work. You always want to write down your formula, and then the next step is to replace your variables. That's usually a common thing to do. So D is what we don't know, but I'm going to throw in my variables, like velocity final, that was 2. I'm going to multiply by my time, which was 20. I'm going to minus 1/2 of my acceleration, which is negative 4.5, times by my time squared, so 20 squared. And that should be it. That's all I really need. There's not really a lot of algebra here other than just using your calculator. Now, if you wanted to, you could do 2 times 20 for 40 and 1/2 times 4.5 times 20 squared and find that. And I mean, you're technically going to add them because you have a double negative. But I don't need you to show all those steps. I just need you to get me the answer now. So this is really a calculator skill. And this is one of the reasons why I want to suggest that using a video like this works really well when we're doing the type of question where there's a lot of calculations. Because if you'd like to, I'm just going to go right to the answer here, and I'm just going to tell you that the answer was 940 meters, but let's draw the meters properly because that was kind of ridiculous, Chris. There we go, meters. Where was I? I was getting off topic because I can't draw a meter symbol. Let's say you get this answer. Awesome. Great. Let's move on. We're done, right? But let's say you don't get 940, right? Now's a great time to put up your hand and say, Chris, help, right? Pause the video, call me over, right? And that's the beauty of this, is if you need that, you're not stopping the whole class. You're literally just stopping you, right? And now you can advocate for yourself and get help when you need it. So, one more thought, though. Actually, this wasn't quite right. We've been talking about significant digits, hopefully. That should be a concept you've learned. And so this right here appears to have 2, possibly 3 significant digits. And as I look at the question stem, all of the example numbers that we were given here, 4.5, 2.0, and 20, have 2, possibly 1. This 20 seconds could actually have 1 sig dig. Probably has 2. So based on that, we need to make one more change. We need to write this as 9.4 times 10 to the 2 meters, or you could write it as 9.4 e 2 meters. And again, this is another good time. Look, if you don't know that concept, if somewhere along the way you just never really clued into how to do scientific notation or how to do sig digs, stop me, let me know how I can help. Otherwise, the other beauty is that if you get this, let's move right on. Let's not waste time kind of pausing. If you get it, let's try something new. I love this idea of asynchronous learning. It really tailors to everyone's individual strengths. Next example, a parachuter deploys his parachute 1.53 K above the ground. So we have a number here, 1.53 K. It looks like we have a deceleration of 6.3 meters per second. And by the way, that is another valid way of writing meters per second squared. Just wanted to show you that. It looks like we also have a time value right here. And we have another distance value. And the reason why I chose an example that looks like this was to illustrate the idea that sometimes when you're solving a problem, you have to be able to pick through and decipher and figure out what is important information and what is not. And this is one of the most important skills that you'll need if you eventually take the Physics 30 diploma exam. It's half critical reading and critical thinking, and that's the most important skill I want to help build in you. You have to understand that there's a distractor in here. One of these two distance numbers is not really relevant. As you read the scenario, it says, look, this guy is free falling. This guy is free falling downwards. And he's going to deploy his chute, and so his parachute's going to open a little bit more, a little bit more, a little bit more, until finally the parachute's all the way open, right? And once it's all the way open, that only took 0.71 seconds. Well, how far did he actually travel during the 0.71 seconds? That's the 34 meters. Not the 1.53 kilometers. That was a distractor. Who cares how high he is above the ground? So let's do the same thing I did last time. I'm going to write out my variables. I've got an acceleration value of negative 6.3 meters per second squared. I've got a time value of 0.71 seconds. I've got a distance value of 34 meters, and I haven't even tried to figure out what I'm looking for yet. So let's keep reading. Determine the man's velocity when he initially opened the parachute. We're being asked for VI. So this is a great strategy for starting a question. Write out the variables that you know. And you don't have to. I'm not going to award any marks for this, but one of the expectations on written work, and this is really part of the communication aspect. Communication is one of those big skills we've been talking about, hopefully. Things like problem solving and grit and critical thinking. Communication is important. And so you need to communicate how you're getting your answer. You can't just tell me the answer's 5. You might be right, but there's not quite as much value in that if you can't show and explain to somebody why the answer's 5. So the first thing you're going to want to do is write down a formula. And this time around, the formula is VIT plus 1/2 AT squared. It's the other formula that's just about like it on there. And from here, there's actually two main ways you can solve this. One of the ways that you'd solve it is by now plugging in numbers, right? So I know the distance, it's 34, but I don't know VI. So I'm going to take VI and kind of leave it there, and I'm going to multiply it by the time, which was 0.71. Then I'll add 1/2 of my acceleration, so negative 6.3, and times it by my time a second time, because you actually use time in this formula twice, and square. Well, at this point here, this is where the math skills kind of come in, is that you need to know how to isolate for VI. And so often at this point here, I'm actually just going to skip ahead right to the final answer. I don't need you to show me step by step how this works, because hopefully I don't come across as being cruel here, but this is grade 8 or 9 or at most grade 10 algebra here. What you really need to do is find what this whole mess is right here as a term, add it to the other side over here, and then divide both sides by 0.71. That's kind of how the algebra works. Okay. Now, if you need some help on this, I will totally help, right? But there's some kids who probably don't need help on this because they understand the concept. That's fine, right? Either way, it's fine, right? That's the idea behind, the idea of like different skills for different people. Monkeys have different skills than the fish, then have different skills than the seal, right? So if you want me to help you with the math behind this, that is fantastic. Call me over, pause the video, I will. But I'm going to verbally say what you should be doing here. I'm going to take 0.5, I'm going to take a half, times by negative 6.3, and times by 0.71 squared. And I got a value. Verbally, I got negative 1.587915. Again, that was negative 1.587915. And that's really what this section right here is that I put in a square. That's a negative number there. Well, to get rid of a negative number, I'm going to add it to the other side. And so when I add 1.58 something 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 to 34, I now get 35.587915. And then lastly, I have to isolate for VI right here, I have to divide both sides by 0.71. So when I divide both sides by 0.71, I get this final answer of 50.123, etc. And from there, all I have left to do is make sure I get the right units, which will be meters per second, and sig digs. And looking at my sig digs, it looks like I only get 3 sig digs, so cut it back to 50. And it wanted a velocity, so I'm going to use a capital D and say he's going down. Seems to make sense. He's parachuting. Okay, now, a couple of thoughts on this. If you need some help, pause the video, call me over. But there's another way you can do this. Some people, they don't like to type numbers in first. They like to rearrange their formulas algebraically, and that's fine too. Again, like, you need to have some algebra skills. It's like what I was saying, like, hockey is going to involve skating. At its fundamental core, you can't play hockey without skating. It's not the only thing you do when you play hockey, right? But it's one of the most important skills. Same thing here. You're going to need to have some math skills in order to be good, successful at physics, right? So if you need help practicing the math skills, let me know. I will help. Here's another way you can do this. Since you know that you're isolating for VI, what you could do is take your formula and take D and subtract 1/2 AT squared. And so what I've really done is it's the same thing. I've taken this whole term over here. I'm subtracting it from the right side to the left. And then you can divide both sides by T. And you could just make yourself a brand new formula for VI. And honestly, this is what we did, right? So if I were to, oh, I need a pencil here. If I were to now plug in those same numbers, it would be 34 minus the half of negative 6.3 times 0.71 squared, all over 0.71 again, and there you'll get your answer. Now, one of the challenges of doing this, though, is you have to know how to use your calculator. If you do it right, you should get the answer 50. And if you're not getting the answer 50 meters per second down, call me over. I'll try to help troubleshoot what you may be doing wrong in your calculator. The most likely culprit is that you have to find the entire numerator before you divide by your denominator. That's kind of the main concept, is that you have to find your whole numerator and then divide by your denominator. And so sometimes kids make mistakes there. But hopefully that made sense. And like I've been saying as we go along, if not, rewind, watch it again, call me over, get some help. Right? The beauty of doing this asynchronously. So let's try another example. We've got a bullet accelerating the length of a gun, which is 75 centimeters. Okay, distance, 75 centimeters. And we have the magnitude. And now that I kind of reread this, I think it kind of was implying that the acceleration was this number here. So the acceleration value is the 5.35 times 10 to the 5. And this time, I'm going to make it positive, because it was accelerating, not decelerating, right? It was accelerating this time. And that's it. I got 2 numbers, which sometimes kids get a little frustrated at, going, whoa, wait, I only have 2 numbers here? One thing that you'll notice about these formulas is that they all have 4 variables. And so regardless of whichever variable you're not working with, you always need to have 4 out of 5. Like this formula here needs A, VF, VI, and T. Right? And this formula needs A, VF, VI, and D. Well, right now, I don't have enough information to use a formula. I mean, I'm looking for with what speed does the bullet exit the barrel, so that's VF. So VF is what I'm looking for. But I don't have enough to use a formula. And again, this is why I'm picking my examples very purposefully. I'm not doing lots of examples because they're all the same as each other. I'm doing examples that have something slightly different every time. And this thing has 2 slightly different. The first one is that there's hidden information here. it is implied that we know the initial velocity. Pause for a second and try to debate or think to yourself, what's the initial velocity? The initial velocity is 0. The reason why it's 0 is because before you shoot the bullet, it's not moving at all. And so the question doesn't tell you that information. But like, that's the point behind physics. It's to problem solve, to critically think, to discover how things work. If someone were to say shoot a gun, it's not going to tell you that the bullet was not moving before you start. You have to be able to logic and reason that out yourself and realize, hang on a sec, the bullet wasn't moving before I pressed the trigger, right? And so that is one thing I wanted to show you. The second thing I want to show you is that this distance right here is not in the appropriate units. The acceleration should be in meters per second squared, and the velocity initial is in meters per second, but this guy right here is in centimeters, which means you got to do one of two things. Either have to make it 0.75 meters, or write it as 75 e minus 2 meters. Both of those work. If you know how your prefixes work, I prefer the second one. Centi, I just know that a centimeter is a minus 2. Okay. Again, if you have questions on that, let me know. But now we're just going to pick out the formula. This one's really straightforward. The formula is VF squared equals VI squared plus 2AD. And the reason I knew that is because I knew I had a D, an A, a VF, and a VI. And if you want to use this chart to kind of help you, look for the column which involves an A, a VF, a VI, and a D. And, well, the one that has all 4 of those is this guy, which means you don't know what time is, actually, which is fine. We don't apparently need the time value on this question. So after we figured out all of those little tricks so far, the question is pretty straightforward, actually. Velocity final squared will be equal to an initial velocity of 0 squared, which does nothing, literally nothing. Acceleration is a positive 5.35 times 10 to the 5 value. And your distance, I'm going to have to write it down below here because I'm out of room, will be 0.75. All I've got to do is square root both sides, and we've got an answer. So grab your calculator, give it a try, see if you get the same thing as me. 2 times 5.35 times 10 to the 5 times 0.75, all square rooted, gives me this number here. And I'm going to go right, actually no, I'm going to write this out. I got 895.8 something something meters per second. First thought, is that reasonable? Well, yeah, it's a bullet. It's probably going pretty fast. That might actually be too fast. I might have made a poor example, but because I think that's actually breaking the speed of sound. But that being said, as long as the question has been designed properly, I probably gave the acceleration too high of a value when I made this example. I mean, it does make sense that it's a large value, though. Just maybe it's too large. Maybe this acceleration was a little bit too big. But anyways, the second thing we do have to consider then is if the answer seems reasonable, like within the scope of reasonability, do we have the right number of sig digs? And this one's going to be tricky. We only get 2 sig digs based on the 75 centimeters. So with 2 sig digs, we get to keep the 8 and the 9, but I can't just make the number 89. It's got to be 8 like 90, but then the 5 rounds up. Long story short, we need 9.0 E2 meters per second. Or, if you prefer, 9.0 times 10 to the 2 meters per second. I don't care whichever one you pick. I like the E2 value. It's faster. I write less, so, you know, physicists are lazy sometimes. Okay, hopefully that made sense. And if not, that's fine. It's okay, right? Rewatch. Ask me for help. We can do this asynchronously for a reason. I'm going to skip through that slide. We're going to go to the next example here. So this one's got another little twist in it. I'm going to give you a little blurb here. It says, studies have determined that the average wet and dry surface deceleration rates, read careful, deceleration, for brakes on a Camry are either 24.2 feet per second or 23.3 feet per second. Well, one of the reasons why this one's kind of goofy is that it's now in feet, and we don't really want to do things in feet. We want to do them in meters. But I gave you a conversion factor here, which is good. So I'm actually going to start with that. We need to convert out of feet per second to meters per second. So here's how that might look. 24.2 feet per second squared. What you need to do is multiply by 0.3048, because that's how many meters there are in a foot. And if you kind of understand how to convert things, what's now happened is I have a correct value in meters per second. 24.2 multiplied by 0.3048 gives me, and I need to save this whole number, but I now have 7.37616 meters per second squared. So that's one value. But look, it actually gives me a second one, so I'm going to use another color, and I'm going to do the exact same math. 23.3 feet per second is apparently how much it takes to slow down on dry surface rather than wet. So same thing, times by 0.3048 meters per foot, which is what's given to you right here. And that's the same thing, 23.3 times by 0.3048. And now I have a value of 7.10184 meters per second squared. Now, I haven't even looked very far at the problem. I mean, why did I get two accelerations? I have an acceleration 1, and I have an acceleration 2. Why do I have two of them? Well, let's keep reading. It says we're going to drive at a speed of 100 kilometers an hour, and it wants to know the difference in stopping distances. What does that mean? Well, it means you need to find the stopping distance under condition set number 1. You need to find the stopping conditions under condition set number 2 and subtract them, because that's what difference implies. So this question, we're basically going to do the same work twice. Now, I actually have to do one more conversion. I've been given a velocity. Now, that velocity was 100 kilometers in an hour. And that was actually an initial velocity, because that's the speed you're driving at before you're going to start putting on the brakes. But this isn't a useful number either. I've got to convert. So again, I'm going to show you kind of how this looks. It really helps if you know your conversions. For example, there are 1,000 meters in a kilometer. And if you do that, you can kind of cancel your kilometers. But that's not enough, because we need to have meters per second. And right now I have meters and hours. So it helps if you know, for example, that in 1 hour, there are 60 minutes. Well, that cancels your hours now. Now I have meters per minute. But I want meters per second. Well, it helps if you know that in 1 minute, there are 60 seconds. And now I can cancel this minute with that minute. And the long story short is that in order to solve this, you have to take the number 100, times by 1,000, and then divide by 60 twice. And so you should, hopefully in your calculator, get this result here, 27.7 repeating. That's your meters per second value. Now, that's confusing to a lot of kids. This would be a normal time in a regular lesson where a lot of kids would give me some funny looks and I would have to like redo this part. And that's what I love about this asynchronous thing right now. If this made sense to you, we're going to keep going. If this didn't make sense to you, maybe you're like, pause for a second, look at the work and see whether you can figure it out yourself, re-watch it again, or if all else fails, ask. Right? That's why I'm free during this time, is I can give more one-on-one help now than whole group help. But if that makes sense, we now have accelerations and velocity initials. I believe we're looking for distances, because that's the whole point, is to look for a distance. And it says we have 2.3 seconds before a collision, so we know the time value is 2.3. So really, we need to pick out which formula to use now. What formula involves velocity initial and distance and time and acceleration? And the answer, drum roll. I made a little mistake. I'm going to have to edit this out of the video here. Where did I finish off here? It looks like what we're looking for now was we've been given a, I was being silly, I did my drum roll and I screwed up. So drum roll. All right, it looks like the formula we need is going to be D equals VIT plus 1/2 AT squared. So let's plug in some values, but I'm going to do this twice. So the first time I do this, I'm going to look for the distance based on a initial velocity of 27.7 repeating, multiplied by a time value of 2.3. Oh, quick note. It has to be 27.7 repeating. You got to keep all those sevens, because that has to do with accuracy. If you start rounding before you should, it's going to cause your value to stop being correct. So do make sure you use 27.77777. Use them all. Our acceleration value. So this is going to change. So I'm going to actually leave a little bit of a blank there. And the reason why is that sometimes I'm going to use the value 7.37616. So right now I'm going to write that in here. Sometimes I'm going to use 7. What was it again? I forgot already. 7.37616. So I'm going to do that the first time around, and I'm going to get an answer. Why don't I do that right now? 27.7 repeating. Times by 2.3. Add a half. Times, oh, I almost made a huge mistake. Negative 7.37616. Why negative? Because we're slowing down, right? All right, and times by 2.3 squared. So I got a value here, and I'm still not going to round yet because we're not done the question. I got 44.3789. And because I'm going to keep using this value, if you have a graphing calculator, I want to show you how to store a number. The way you store a number is you press the button second, which is like blue or green or yellow. No, you don't even press that button. I take it back. Don't even press the second button. You literally look for a button called STO. It's right above the on button. It's STO with a little arrow. And what you're going to do is you're going to press that button, and then you're going to press, like, say, the alpha button, which is green or yellow. That's the one, green or yellow. And then pick any letter on there, like, say, A or B or C. So if you do, say, alpha A, what your calculator should appear as is it should literally say ANS arrow A. And what that's going to do if you press enter is it's going to make every time you use the letter A, it's now going to be that value, that whole value with all the numbers stored. And that's really, really valuable to have when you're doing multiple calculations, because now you don't have to write down the whole value. Anyways, I now have to redo the exact same thing, but now I have to use the other acceleration value. Remember how there were two deceleration values? So this is like the first one, distance 1. Now we got to find distance 2. So all I'm going to do is I'm going to erase this number right here. You get sound effects. You really get a show. Throw in a negative and make it 7.10184. 7.10184. And really, you're doing the exact same math. You're just doing it a second time with a different deceleration value. So 27.7 repeated times by 2.3 plus a half times negative 7.10184 times by 2.3 squared. And for my second distance, I got 45.1045, etc. And I'm going to store that, since the first one was letter A, I'm going to store that as letter B. So I go store alpha B. For me, that's apps on my calculator. And so now I have these two values here. Well, now my goal is to find the difference between them. So now I'm just going to take these two values and subtract them. So take your B value, subtract your A value. And I don't really care what letters you're called, but like just take these two numbers and subtract. So take B and subtract the 44.37 number. And hopefully you'll get something like this, 0.7255. Now we can do sig digs. So sig digs, looks like I'm seeing 2.3 seconds is 2 sig digs. So let's make it 0.73 meters. And then, is that reasonable? I think so. I mean, look, the difference that we were asked for here is what's the difference between braking on wet and dry conditions? And it's about 3/4 of a meter stick, which, okay, that doesn't sound like a lot, but if you're worried about rear-ending somebody, an extra meter stopping difference is a huge deal. I mean, that's why we wear, it's why we're supposed to have snow tires on our car in the wintertime, because it's supposed to help with your stopping distance. So it's actually kind of logical. Okay, same deal as always now that we've solved for our final answer. If you'd like to rewatch, pause, ask questions, or move on to the last example. Got one left. So here's our last example. We have an F-22 traveling 97 meters per second, and it kicks in the afterburners. Let's start right now what we know. It's going 97 meters per second, and it looks like it's accelerating. So that means we have a velocity initial of 97. We have an acceleration rate of 26 meters per second squared, and I see a distance here of 3.2 kilometers. I already know, though, that that's not the right unit, so I'm going to just times by 1,000 in my head and say I know my distance is 3,200 meters, and it wants to know time. This is what makes this question kind of challenging, is that there's actually two main ways of solving it, but there's a problem with this one. It's a struggle. When you start figuring out which formula to use, it ends up being d equals VIT plus 1/2 AT squared. And so when you start plugging in values, you actually get this. You get 3,200, and it equals VI, well, that's 97, times by time, plus 1/2 of your acceleration, which is 26, times by t squared. How do I solve? I have a variable for time right here, and right here. Well, there's two main ways of doing this. Before, though, I want to try something with you. And I mean, you don't really have to do this if you don't want to, because you're watching a video, but I'd like to suggest try to figure this out by yourself first. Pause the video, spend a couple of seconds trying some things, and see whether you can figure out how to solve this puzzle, because it's mostly a math problem at this point here, right? And then once you're ready, or if you don't really want to do that and just want to move right on, then you keep watching the video. But maybe take a second and just try to think, how have I ever in the past learned how to solve for more than one variable? And actually, this may not be fair, because it means that you have to have completed a Math 20-1 or 20-2 course. Okay? So if you're in Math 20-1 or 20-2 right now, I'm so sorry. Ideally, you should take that before physics, but I mean, okay, it is what it is. But this is a quadratic formula example. For those of you who know how the quadratic formula works, it works like this. If you ever have something in the form ax squared plus bx plus c equals 0, you can use the quadratic formula of negative b plus or minus the square root of b squared minus 4ac all over 2a. And that will help you solve for x values. And that's very useful whenever you have something with a power of 2, a power of 1, and a constant term. And guess what, guys? We have a power of 2, we have a power of 1, and we have a constant term over here. So if you know how to use the quadratic formula, this is actually a time where you do that. And if you haven't learned how to use the quadratic formula before, there is an alternate way of solving it. But ideally, you should be taking Math 20-1 or 2. You learn about this in either of those two courses at some point. So hopefully you've already learned this. But if not, I will show you. So here's how this looks. I'm actually going to take 1/2 of 26 and make it be 13 t squared. And I'm just kind of rearranging the order. Then I'm doing 97t. And then I'm going to bring the 3,200 to the other side and make it minus 3,200. And all of this is now equal to 0. And now I can use the quadratic formula. So if you know how, it looks like this. Negative 97 plus or minus, because 97 is your b value. 97 squared, because again, that's your b value. Minus 4. Your a value is now 13, because it's half of 26. And your c value is negative 3,200. And when you're done, you divide it all by 13 times 2. 2 times a. Okay. So again, that formula, in case you missed it, was negative b plus or minus square root of b squared minus 4ac all over 2a. And this is a, your first term, b, your second term, c, your constant term. Now, here's the thing. You're going to get two answers when you do this, but only one of them is logical. I'm going to solve them both in my calculator here and just write them down. So I'm going to do 97 plus the square root of 97 squared minus 4 times 13 times negative 3,200 divided by 2 times 13. And so I got an answer of 12.3. But I should get a second answer if I do negative 97, subtract the square root of 97 squared, minus 4 times 13 times negative 3,200, and then you divide by 2 times 13. I also get negative 19.8. And if you've taken, especially Math 20-1, you might have learned of something called an extraneous solution. You can't have a negative time here. So we have our answer, 12.3. And with SIGDIGs, it's actually just 12. So 12 seconds. 12 seconds for this jet which is traveling 97 meters per second, to travel 3.2 kilometers when the afterburners are accelerating it at 26 meters per second. So that is a challenging question by far, because it involves some problem solving. It involves a huge math overlap, which you may or may not even have learned. And yeah, it's challenging. So let me show you one more way of solving this. Let's say that you haven't taken Math 20 yet, which is fine. Okay. You will learn how to do the quadratic formula at some point, and it is something that you need to know. Okay. And I can help with that, by the way. I've taught math before. But there's an alternate way of solving this. Let me show you that. So remember, the answer was 12 seconds, by the way. The alternate way of solving it is to not solve for time first. It's to solve for the remaining variable. The one variable we didn't solve for is velocity final. And so rather than solve for time, I'm just going to omit time for a second. Let's use a different formula, and let's solve for velocity final. Let's use the formula velocity final squared equals velocity initial squared plus 2AD. So I'm actually going to solve my question by solving a different question. So if I plug in the velocity final as what I don't know, I'm going to leave that. Velocity initial was 97. We'll square it. We'll add 2 times 26 times 3200. And when I'm done, don't forget you're going to be square rooting both sides. So velocity final, I'm now solving. 97 squared plus 2 times 26 times 3200 square rooted gives me a final velocity of 419.29, etc. meters per second. That actually kind of makes sense. That's going faster than the speed of sound, but this is an F-22. The speed of sound, by the way, for reference, is about 330 meters per second. So this thing must be going at least Mach 1, which makes sense. It's an F-22. So, I mean, it's in the ballpark. We need to save this value, though. So I'm going to go store as alpha A and just save this as my A answer, because I'm going to need that in a second, because I now know my velocity final. My velocity final is what I've now picked as letter A. Well, now that I know velocity final, I now know 4 of my 5 variables. Let's pick a different formula that involves time. For example, why don't we use the formula that looks something like this? Let's use the formula where it says your acceleration is equal to your change in velocity over your change in time. And I'm going to rearrange this one by, I'll do the rearranging first. I'm going to go change in time is going to equal to your change in velocity over your acceleration. So hopefully that made sense from a math perspective how I rearranged there. If not, call me over, I'll give you a quick tutorial. But I'm going to do one more thing. I'm going to say that my change in velocity is really my final velocity minus my initial velocity. That's how much difference there's going to be. So hopefully this makes sense, because again, when I make a video like this, I'm going to plow through a little bit faster than normal. So there's really no wait time. So you pause if you need to. But now I have all the numbers I need. I know my velocity final. It's what I designated as letter A, the 419 meters per second. I know my velocity initial, it was 97. I know my acceleration, it was 26. This ain't so bad. Take your answer, minus off 97, divide by 26, and what do you know? I got 12.3, which is 12 meters. No, we're in time, 12 seconds. So there, I showed you 2 ways of solving a question like that. And that's a pretty challenging one when you're using this formula right here or this formula right here. If you're ever solving for time, it involves some pretty good math chops. You need to either know your quadratic formula or you have to use 2 steps. Now, that being said, either way you should be able to do, because we are going to do lots of physics questions over the next, however long you take physics, whether it's just this year or even physics 30, where you have to use like more than one step. So, I mean, using more than one formula is not going to be uncommon for us. But also, like, math is a prerequisite. Like, you need to be either co-taking or you're going to take math 20-1 or 20-2. So you got to learn the quadratic formula either way. And that's it, guys. That was my last example. So we're going to do graphing next day. So here's what I want you to do. If that made sense to you, that's fantastic. It took me 50 minutes to make this video. We normally have an 80-minute class minus however long I talked for, because I'm sorry, I do talk for a while, right? So that means that maybe you have like 20 minutes of pause time, right, where you've been rewinding or pausing or asking questions. And so keep doing that, right? If you need more time, then rewind, watch the video again. Watch it again tonight. Please ask me for help, though, right? I expect that you're going to want to ask me questions. When you're done, I'm probably going to tell the whole class, but I'll say it here too, that you've got some assignment questions to work on. And so although the assignment doesn't have to count, because your progress log is a unique way in which you calculate a very unique mark to yourself, and you don't even have to do the first assignment, I strongly recommend that you should probably try it. Even if you do poorly on it, it doesn't have to count. But, I guess you could just do nothing. But you shouldn't, right? You should practice this a little bit. I'm not going to make you do questions 1 to 60 in the textbook. I don't think that's helpful. But doing a few targeted questions for reinforcing things, that's a good idea. So, anyways, I'm going to stop the video because now we're up to 51 minutes. Good job, Chris. Stop talking. And yeah, we'll talk to you guys later, and we'll do another video another time. I hope this was valuable to you guys.